let's discuss the tree training algorithm. So at the moment, we've talked about what are the metrics the algorithm is going to use. What are the metrics that are going to decide this is a better split point than this other consideration. For classification, we have two options, entropy or the Gini impurity. They're going to work mostly the same, so using one or the other isn't going to change our model's performance too much. For regression, we have the variance, the overall drop in the variance. Now we know what metrics are going to use to say one split point is better than the other, but how is it deciding all the questions, all the potential questions to ask? For each feature P, it's going to construct a threshold. So let's go ahead and examine that. Let's go ahead and visualize it. So for each question, for each feature, it's going to go ahead and draw a line. So this is feature P. So this line represents the range of the values for that feature. So let's say this feature is going to range anywhere from 0 to, let's say, 5. And it knows this range because this is the range of all the possible values for this feature for all the points that exist in this current node. And then using all the distinct values for this feature at this node, it's going to construct these thresholds. So these ticks here. So these are the ticks. Each tick represents a distinct value for this feature for all the points in this node. Then it's going to use these ticks as a threshold. In other words, it's going to ask, what if I used this feature to separate my space? In other words, move all the points into one node that has a value less than here, than this value here. All the ones that have a value greater than this threshold, go move on to the right node. Or maybe I should use the threshold at this point. Let's use this value for this feature to perform the split. So these are all the different possible questions it can ask. And this process is repeated for all the features that exist for my data set. So this is how it considers all the different candidates for the split. Then it considers for each candidate, what is the error metric? What is the reduction in the error metric? And which one is the best to use? Which one will give me the greatest drop in my error metric right now at this point? This is called a greedy algorithm. So the node splitting process is greedy. And we've seen some examples of a greedy algorithm before. Where was another example? What was another situation where we saw a greedy algorithm? We saw an example of a greedy algorithm with respect to gradient descent. In gradient descent, we're going to move in our space the direction with the greatest drop in the error metric of our cost function. So we're always looking, what is the locally optimal choice right now at this point in space? Same thing for this node splitting process. It's going to choose a split point that will result in the greatest reduction of the loss metric at the moment. So what might happen when we use a greedy algorithm, there might be a suboptimal choice. So it's not going to consider, if we have a greedy algorithm, it's not going to consider any suboptimal choice that may set up an overall better choice in later iterations. It's going to say, what should I do now that's going to make me the most money? What should I do now that's going to drop the error metric the most? So that might be a problem with greedy algorithms. Greedy algorithms may not always converge to the global minimum. But the advantage behind greedy algorithms is that they'll often have better time complexities compared to algorithms that may result in more optimal solutions. In other words, the greedy algorithms tend to be simple. They tend to converge faster. If we were to use them, we get an answer a lot faster than if we used a more sophisticated algorithm that might consider making suboptimal choices early on that might open us up to a greater optimal choice later on, plan ahead. But those algorithms are going to be more computationally expensive. They're going to take longer to run. And yes, they might give us a better answer than the greedy algorithm, but then the question is is that extra computational time worth it? Is it worth running more calculations, running more examples, understanding what's a better choice to make? Will that gain us anything? Might give us some model performance. Might get a small boost in model performance, but then the model's going to take a long time to train. Might be intractable. Might not get training times that would work out for us. So we see here a trade-off. Using, trying to figure out the global minimum, trying to find the global minimum might take forever, might take a long time. But if we use the greedy algorithm, we'll get an answer that's just as good. Just as good for our purposes. Might be, yes, not slightly worse, but it's going to be a lot faster to obtain that answer. So decision trees are going to use a greedy algorithm for its node splits. That's perfectly fine for us. We're okay with that trade-off. Now let's consider some of the hyperparameters, some of the key hyperparameters for a decision tree model. Now when we talk about these algorithms, we're getting an in-depth view of how they work. We need to see what are the hyperparameters are involved. Because these are the bells, these are the whistles, these are the knobs that we have control over when we try to tune our model. So we got to see what's available for us to tune and how does tuning them work out. In other words, if we increase one hyperparameter, how does it affect the variance bias trade-off? So let's discuss that for decision trees, some of those key hyperparameters. So we have max depth. So max depth is going to control the growth of the tree. How deep can it grow? As our tree gets deeper, our model gets more adaptive. We create more parameters that can fit to the training data. That's going to be good up to a certain point. At some point, if we have a tree that is too deep, it's too adaptive. It's going to learn the signal in the data, but it's also going to start fitting the noise. It's going to start learning the idiosyncrasies of our training data. We don't want that. So at a certain point, increasing the depth is going to hurt the model's performance. So in this example here, increasing max depth will increase the variation error of our model. Let's look at the max features. This is another hyperparameter we can control for decision trees. So there's a number of features to consider when deciding the best split. In our discussion before, when training the algorithm, training the model, it's going to look at the thresholds, all possible thresholds for all possible features. They're going to use those as candidates when performing a split. But instead, the algorithm can say, you know what, I'm not going to consider all the features. I'm only going to consider a subset of those features. For example, there might be 4 features in our data set, but I'm only consider, let's say, 2 of those features when deciding what is the best candidate to use to split my nodes. Given this definition of max features, what do you guys think? How do you guys think this will control the bias and variance? Will increasing the max features, will that lead to a high variance model or a high bias model? Will it tend to underfit or will it tend to overfit as we increase the max features? In other words, if we consider all the features we have in our training example, will that be prone to overfitting or underfitting? If we consider less features to perform a split, then what's happening there is that we're going to have a simpler model. We're not considering all possible candidates to perform a split, so that will tend to push our model towards the underfitting side, to be less adapted to training data. So let's consider another hyperparameter, the min sample split. So the minimum number of samples required to consider a split on an internal node. In other words, if a node, internal node here, doesn't meet the criteria, this minimum criteria of samples, of observations in this node, it's not going to further split in that node. So given this definition of min sample split, how do you think it's going to affect bias and variance? If we increase the min sample split, we're going to have a simpler model or a more complicated model, a more adaptive model or a less adaptive model. As this minimum number increases, then more and more nodes, more of these internal nodes, we cannot further split on them. So the depth of the tree is going to be stunted at that point. So it's not going to be able to grow. And since we're not going to allow our model to grow, it's not going to be as adaptive. So increasing the min sample split will push the model more to the underfitting side than the overfitting side. We'll push for a simpler model as opposed to a more complicated model. So if we have a situation in which our model is overfitting, then we might consider playing around with min sample split. Specifically, since we are overfitting, we want to increase the min sample split. Have a model that is at the right point where there's neither underfitting or overfitting. So this is a knob we can control to tune our model, get the most out of it for our task. We have another related hyperparameter. It's called min samples leaf. But this one's defined slightly differently. In this case here, it's the minimum number of samples required for a leaf. So if there's a split that we could have performed that would have resulted in a leaf with less than the minimum, then it's not going to happen. So now the question is, how is this going to affect bias and variance? A simpler model, a complicated model, an underfitted model, or an overcomplicated model? Same process above, or same answer as above with the min samples split. As the min number of samples to be a leaf increases, that's going to prevent our tree from becoming complex, from growing. So increasing this value will lead to a underfitted model, but push away from an overfitted model. So we'll reduce the variance and go towards a bias situation for our model. To see the importance of for a model, consider the hyperparameters we have available for us, and actually go through the discussion saying how does this affect bias and variance. So we get a good idea of how well our model works, how the model works, what are our options, and how do the model behavior is affected by changing the values for those options, for those hyperparameters.